Let's understand the term buoyancy. So buoyancy is the net upward force applied on the object which is immersed or is floating on a fluid surface. Now what will be its value? What will be the force? What will be this net upward force value? Let's try to see that. So let's consider fluid inside some container. Okay, so this is, let's say, the fluid inside some container, and a body of some arbitrary shape, let's say, is immersed inside this fluid. So the question is, what is the upward force that this body would feel due to the fluid? Okay, so to study that, let's consider an elemental volume element in this body of volume. So this is elemental volume element with volume dV. Okay, so now from our knowledge of hydrostatics, we know that the fluid will exert pressure from this side as well as from this side on this volume element, correct? What will be the value of this pressure or the force due to this pressure? So let's consider this depth to be h1, and let's consider, so let's say this depth is h1 and this depth is h2. So the force, the pressure value applied on this surface of the fluid element, the volume element, will be h1 rho g plus p atmosphere. Let's say this is the free surface, this is your air. Okay, so this value will be h1 rho g plus p atmosphere. And what would be this one? This would be h2 rho g plus p atmosphere. Now rho is the density of this fluid. Okay, so now what will be the net force on this volume element? So since we know that h2 rho g will be greater than h1 rho g, the net force on this volume element, the net force on volume element dV will be equal to, volume element dV is dF, which will be, let's say, this, the coordinate axes are chosen such that this is, let's say, z, and this is, let's say, y. So it will be dfz. It would be h2 rho g plus p atmosphere minus h1 rho g plus p atmosphere, and this will be upwards, so it will be along minus k hat direction. Okay, so let's say I'm just interested in finding the magnitude of this value. So this is dfz and this is along minus k hat. Okay, so just simplify this term, p atmosphere would cancel out, and this would be h2 minus h1 times rho g. Okay, correct? Oh, so this is the force value, so that's why we have to multiply the area of these surfaces also, right? So we'll just multiply the area. So let's say the area is dA and this will be multiplied with dA. So this will be the force acting along minus k head directions. Okay, minus k direction. Now what will be the total force on the z total force along minus z direction? That would be simply dfz. So let's integrate this term. So h2 minus h1 into rho g into dA integral. Okay, so now rho and g, they are independent of the volume element chosen, so we can take them outside of the integral, and this would become h2 minus h1 times dA. Okay, now this h2 minus h1 times dA is what? It's simply the volume of this element, so we can write this as rho g times dV. Okay, and the integral of this dV would be nothing but the volume of this body which is immersed inside the fluid. So from this we get the buoyant force, which is nothing but the net upward force applied by the fluid of density rho, and this is equal to rho g times the volume of the body immersed inside the fluid, right? So let's say if this body was not in this case I have completely immersed the body, and let's say the body was not completely immersed inside the fluid. So let's say the fluid was like this, okay, and my body, let's say if it would have been like this, then what would be the net upward force? So that would be, let's consider this example and let us try to understand whether the volume that we put here is actually the volume of the whole body or the volume which is immersed inside the fluid. So I have just written it from my previous knowledge, but let's try to derive it. Okay, so now again consider this volume element. So let's consider this volume element, let's say like this. Okay, now what will be the pressure acting on this? So let's say this depth is h, the pressure acting on this volume element will be h rho g in the upward direction, right, plus p atmosphere, and here only p atmosphere would be acting. Okay, so what would be the net upward force? So net upward force would be simply h rho g times dA, where dA is the area of this part, right? Now, so this net upward force on this elemental volume is actually dF. Now to find the total upward force, we'll simply integrate into this dF, which would be nothing but rho g times h dA integral. Okay, so now what is this h dA? H dA is the volume of this part of this volume element which is immersed inside the fluid. Okay, so the integral of this volume element, so rho g times dV, where this dV is the part of the volume element immersed inside the fluid. So if I integrate over this dV, I will get a V, and that V would be the volume of the body which is immersed inside the fluid. Okay, so from this derivation we now derived this expression, that buoyant force is nothing but the net upward force by the fluid of density rho, which is displaced by this body. So when a body is immersed inside the fluid, the amount of volume, so this would be the amount of volume that this body would displace, and this the weight of the fluid that it has displaced will be magnitude wise equal to the buoyant force that this fluid will apply on the body. Okay, so this rho g times V can also be written as mass of fluid displaced by the immersed part of object times gravity, right? Or this mass times gravity is the weight. So we can also write that this buoyant force is actually the weight of the fluid. The buoyant force will be magnitude wise equal to the weight of the fluid displaced by this immersed by the volume which is immersed inside the fluid. Okay, so this is what a buoyant force is. Okay.